Hey, let's start the polynomial journey. What's that? A polynomial. Whoa. Well, quadratics are the gateway to polynomials. A quadratic function is the simplest polynomial. Poly, many numbers, if you like. Many powers of the variable, x squared, plus 2x, plus a number, if you like. A quadratic, a function with many powers of the variable. Okay, so you've got to have more than one power of the variable. So 2x plus 3 is not a polynomial, it's a linear function. So the first one is quadratics, and they are the gateway because quadratic theory, all that we did before over here, and I hope you can remember some of that, can be built upon to build bigger and bigger polynomials. Cubics are what we're going to talk about here. Here's the title over here, Introducing Cubic Polynomials. And we can build on that. So let's have a look at some of those things. And I think the most important thing is to say, well, okay, here's our parent function. Y equals x squared is a simple quadratic. And if we then take the formula and put x take 3 squared take 4, I hope you remember that. The idea of this form, the perfect square form, gives you a vertex of hk. So the vertex is hk. So if we have this function, it's been moved across to 3, neg 4. Okay, the opposite sign of that negative there will be the vertex value, 3, neg 4. Now, that's a common property with functions in general, that translation idea. And I'm going to prove that for you in a minute. Let's have a look at cubics though. Here's the parent of the cubics, x cubed, the simplest cubic. And it looks like this. And you could plot that on the calculator. Each time you cube a value, let's take this one over here. X is neg 1. Neg 1 cubed, neg 1 by neg 1 by neg 1 is neg 1. So it gives us our point here. And over here at 1, 1 cubed gives us 1. So we can plot points like that. Because it's a cubic, it will go below the axis, unlike the quadratic. Because up here, a square of any number is always going to give you a positive answer. Okay, so it's a different looking graph. But the same sorts of things apply now. If we have x take h all cubed, so we're changing the x cubed to x take a constant, and then we add k, what's going to happen? Same idea. It moves h and then k. This is a common property with translations of functions. So we're going to pick up on the quadratic theory being the gateway, here we are, to further polynomials, and we're going to build on that stuff. So let's have a look at that translation idea. Here we are, the translation of any function, y equals f of x. Let's take y equals f of x. And let's translate it, let's say, in the x direction, translate in the x direction by h, and in y by k, let's say. Okay, what are the transformation equations? My new position for my point, my new x, will be my old x moved h. My new y will be my old y plus k. So that's how we've moved the points. So the original point xy on the Cartesian plane has been moved to x prime, y prime, x dash, y dash. So let's rearrange this, rearranging the equations to actually relate the old y and the old x to the new one. So let's subtract h from both sides. So the old x is your new x take h. The old y is the new y take k. Now, therefore, let's substitute these old values or old expressions for the original points on the plane. Substitute these into the original formula. And let's look at what happens. Something interesting happens. The old y is the new y minus k. So I'm replacing that. And equals function, no matter what function it is. And my old x will be my new x minus h. Are you starting to see it? So now adding k to both sides, my new y is my function in my new x take h plus k. Oh, do you see it? If you translated hk in any function, the x term, the new x is x prime take h. Well, my new x is x prime. My old x, I've replaced it by x prime take h. And these are the effects. So it doesn't matter what f is. If I was to take x to the fourth, let's take y equals x to the fourth. Then I translate this, let's say, h in the x and k in the y. Because this is a general proof here, the new function would be x take h to the fourth plus k. Alright, the x term changes by subtracting the directional translation, then adding k on the end. And why is it x take? Well, here's the step up here, isn't it? When we rearrange the transformation equations to substitute the old x and y into the original formula. It's x take h and y take k. And then, of course, we move the k across. So that becomes a positive on the other side. Alright, so can you track that through? Interesting. That's a bit beyond this course, but I think it's a powerful bit of mathematics here because it enables you to move the graph of any, state the graph of any function under an x and a y translation, and to work backwards, in fact. Let's see if we can do some problems with it. Excuse me. So here, graph on the same axes, x cubed and neg x cubed. So we're starting to look at various cubics based on the parent y equals x cubed. So here's x cubed coming down here, dotted line there. If I multiply in here by a negative, these values multiplied by a -1 would become negative, wouldn't they? Instead of plotting above the axis, they will plot below the axis. And similarly here, these are all negative values. If I multiply it by neg to get neg x cubed, they will become positives. Okay, so neg x cubed is what? It's a reflection in the x-axis. Reflection in the x-axis, if you like. All the positive becomes negative and the negatives become positive. Fairly easy to understand if you think about that. Okay, let's graph these two, x cubed and this one. Okay, so there's x cubed. Oh, that's a +2 shift. Here it is. Goes across there and then down 1. So that key point, it's called a point of inflection, we'll learn about later on, goes to there. This point here will go across 2 and down 1. So we can actually move a few points and track out the new position, the translated position of x cubed from these numbers here. It's across 2 and down -1. Okay, so please remember the idea of any function moved h in the x and k in the y. That's what happens to the formula. Whatever the f is, whether it's x to the fourth x cubed, it is now replaced by this, and we add k at the end for any hk translation. X is h, x translation is h, and the y translation is k. Okay, I want you to try to use that idea without a calculator, without plotting points, to move x cubed around according to this. So just starting out on cubic polynomials, building on some quadratic ideas as well, things that we've learnt before. Okay, have a go, pause the presentation, and I'll show you the answers now. Okay, so here they are. It's all coming from Hayes and Harris, so useful to have that book handy by to check what you've done there. So you should try all of these so you get familiar with what's going on. Alright, let's go on and have a look at some other things that we can do, again building on our idea from quadratic theory that we've done before. Okay, write this in general form. That's the expanded form. In the polynomial form, many powers, expanding it out. Okay, so here's our function. Now what does that mean? means x take 1 by x take 1 by x take 1. Okay, but you could call it x take 1 by x take 1 squared. So then, can you go directly from that to that? I hope so. A take b all squared is a squared take 2ab plus b squared. Okay, otherwise you have to do a FOIL, x take 1 by x take 1. Okay, now we've got to multiply all this out now. I don't know why they've done that, they put it over here. How do you do that? Well, it's a FOIL. It's that by that, that by that, that by that, and then do the same again down the bottom. And we get all these terms here, which comes to this thing. Okay, so coming back over here, putting that in place of those, we get this big answer here. So it's really just lots of FOIL. First hours, inners, last, that sort of thing. Only here there are 3 terms, so it's not really FOIL, but it's every term in the first bracket multiplied by every term in the second. So you need to be careful with that. And maybe try a few of these, you might not try all of them. Be careful with the fractions and the negative outside of the bracket, keeping it right out the front there. Alright, have a go, see what you think. I'll show you the answers now. Okay, here are all the expansions. Okay, so see if you get a few of those right. It's very important to do that expansion carefully and to watch the signs, as I said before. Let's keep going. Now, I've got something here for you, a question. If the quadratic function, so going back to quadratics, if the quadratic function factors to that, it's got zeros of x is 2 and x is 3. I hope you agree. Zeros are where the function equals 0. Or if you like, where it cuts the x-axis, same thing. So when we have a function like this put equal to 0, it's a product of 2 factors is 0. Then the null factor law comes into action, doesn't it? Null factor law. A product can be 0 only if one of the factors is 0. So either this is 0 or this is 0. Just check it. X take 2 equals 0 implies x is 2. And of course, doing the same thing for x take 3, we could have x is 3. A bit of revision of quadratics. Now this is the interesting gateway idea. So using that idea, can you say, if I have a cubic factored like this, what will the zeros be? When will that function be 0? Can you see, we've just added another factor. But the null factor law still comes into play. It's going to be 0 when either that is 0, or that is 0, or that is 0. So see, if you've accumulated this knowledge of maths in sequence from quadratics, you have tools now to extend to cubics. That's very, very important. We don't want to reinvent everything. We're just adding to it, and if we added another factor, what would it be like? Could we maybe do a sketch here? What would our sketch look like? Was going through at 2, 3, and 4. Now I'll tell you it goes up at the end, right? It goes there. So it's got to go through these. It'll look something like that, I think. Do you agree? We'd have to check values out here to see whether it went up or down. It actually goes upwards. But you could track another one through here, which is downwards, but it's not actually that one. And we'll talk about that later on. Okay, so how powerful is that? That factored form giving us the zeros, and therefore hinting pretty strongly at what the graph might look like. Okay, here's another question for you. Have a look at this one. And what about this quartic? I put another factor on the end. What do you reckon? Where would its zeros be? When will this function be 0? Which are, of course, the same as the x-intercepts. What do you reckon? Null factor law again. X is 2, 3, 4, or 5. So that's going to go through the axes at the x-axis at 4 different spots. Let's try to draw it. It actually goes through, what are we at? 2, 3, 4, and 5. So it actually goes like this. Okay, X and Y axes there. Okay, it looks like that. It's a bit more symmetrical than that. I should have about like this here somewhere. Okay, pretty powerful stuff, isn't it? Minimum amount of calculation. If you have the factored form, you can say a lot about the graph because you've got the intercepts. Okay. I guess you could also find the y-intercept up here pretty easily, couldn't you? By subbing in x is 0 into the formula for the function. Okay, let's do that. If x is 0, that'd be -2, by -3, plus 6, by -4, -24, by plus 5, which would be -4 by -5, sorry, would be plus 120, I think. Yeah. So here we are, let's do it. 2, -2 by -3 by -4 by -5. Yep, and so it's going to be plus 120. So we could do that, substituting x as 0 in each of them. So it's way up here somewhere, up the axis. So that's pretty powerful, those two little things, the zeros, where it cuts the x-axis, and subbing x is equal to 0, the y-axis, and just checking it out. Okay, are you ready to try your hand now at some of these? So there's what we've just established, coming from Hayes, and Harris. The zeros of any polynomial are values of x which make the y have a value of 0, and therefore that's where they cut the x-axis. So here you are. If you have that form, you can say those, alpha, beta, and gamma, are where it cuts the x-axis. And you could extend it to other polynomials. You could extend it to higher degree polynomials as well. Higher degree polynomials. We just did a fourth. We could do a fifth, etc. But can you see how the quadratic idea, what we do there, opens the gate to all the other polynomials, if you like? Okay, so using axes, intercepts only. Sketch the graph. So here we go. We're going to use these. So what are the intercepts? Put the first one equal to 0, -2. Second one equal to 0, 1. The third one equal to 0, 2. Okay, then when x is 0, sub that back into our original function up here. So it's a half, and then the next bracket is 0 plus 2, or just 2. 0 take 1, or just -1. 0 take 2, or just -2. Multiplying that all out, you get 2. So it's got to go through this point and these points. So you can see it's going to come down there and somewhere turn around. We're not worried until you do the calculus next year of those, finding those points there, the turning points, theoretically. Let's look at this one here. Putting x is equal to 0, and then this one equal to 0, x equals 2 twice here, because you've got two values, so x take 2 by x take 2 equals 0. So you can get 2 from each of the brackets. And you might remember from quadratic theory that means it touches the x-axis at 2. And put in x is 0 in here and here, so it's going to be 0. So it goes through here, then it's got a touch there. Okay, so it's coming down, touching, and then turning around. So this repeated factor, giving you a repeated 0, means a touching point on the x-axis. We did this, we just revised that back in quadratic theory. If we have y equals x take 1 squared, and you could say here, well, that's an x translation, isn't it, of y equals x squared. So if we do that, there's y equals x squared, and it moved across 1, so it's over here, and it still touches there. Okay, remember that. So this repeated factor means it touches the x-axis. Are you ready to have a go now? Let's go down. I'll ask you to have a go at these. I think you probably should do all of those to get the hang of it. Building up some knowledge now. Try to remember the ideas as they come along. Maybe make some notes about these axes intercepts. Okay, pause the presentation, have a go. I'm going to show you the answers now. We're coming down. Here's some answers for you. Okay, did you get those right? Okay, the idea is to try and do it just on the axes intercepts. You could sub in some more points, but the idea is to try and base it on that. Okay, let's move on then and have a look. Okay, now we're going to graphs backwards and forwards. Now what about if we know the zeros, can you produce the factors and therefore find all of the family of cubic polynomials? A 0 of 1 in this first one means x take 1's a factor. 0 of neg a half means x plus a half. Remember the opposite sign, because you're going to be putting each of the factors equal to 0 under the null factor law. Now this one's more easily done with 2x plus 1. Okay, so that if you put 2x plus 1 equal to 0, you get 2x equals neg 1, x is neg a half. It's just a neater factor there than having a fraction in it. 0 of 2/3 is going to be x take 2/3 or 3x take 2. The bottom of the fraction is the number in front of x, isn't it? Because you can see when you put the factor equal to 0, 3x would be 2, dividing both sides by 3, it ends up there. So that's the bottom of the fraction, and that's the top of the fraction, if you like. Okay, so we've got these factors going back from zeros to factors. But just remember there's a whole family, aren't there? Because if we were to draw the graph here, let's try and draw a little graph. We've got what? 1 neg a half and neg a half and 2/3. Oh, hang on, let's change the scale here a bit. Let's get rid of that. So here, let's go 1 2/3 and neg a half. So with this one, what we're going to say is there could be various steepnesses. It could be actually fairly flat, or it could be quite steep. So, okay, so this one here, A is going to be larger. Come over here, the number in front there, it's going to be steeper. So we've got to remember there's a whole family all having these same zeros or x-intercepts. So we put that in front to represent a whole family, and then we say A is not equal to 0. Because no function would exist if it's 0 times those brackets. It's just y equals 0. So we made that specification. What about the second one here? 2 is a double root, double 0. So therefore x take 2 squared is a factor. So it's a touching point. For 0 of a half, factor is x take a half or 2x take 1. So the function is this one here, and you put an A in front. If you knew a point on the curve, you could evaluate that A, couldn't you, from the quadratic work that we did. I think you should try all of these and see if you can write down the polynomial expression, and then maybe also do a bit of a sketch graph. Okay, not required in this question, but you might just try it out. Okay, pause it and have a go. I'll show you the answers now. Here are the answers for that particular set. Don't forget the A, okay, because it's a family. And then put A is not equal to 0 then. Alright, let's keep going. A little bit more to do, and so you feel pretty comfortable with cubics. Okay, now, finding the equation given the cubic. Where would you start? Well, I think we're doing this pretty well. We've got the zeros there. Neg 1, 2, 4. So the factors are, don't forget the A, a whole family. X plus 1, x take 2, x take 4. Now we do have a y-intercept when x is 0, y is neg 8. So let's sub that in here. So put in 0 in place of x, it becomes 1. Put in 0 here, that's neg 2. Put in 0 here, that's neg 4. Has to come to neg 8. When we solve that, we find that A is neg 1. And that's why it's going downwards there. because you've multiplied for those large x values, it will be effectively negative x cubed, etc. Okay. Alright, what about this one? Touching at 2/3 indicates a squared factor. Okay, well, here it is. It's at 2/3, so it's x take 2/3 squared, or this time it's much better to call it 3x take 2 all squared, because it is touching there. It's a square, so it's touching. And then this one, x plus 3. Don't forget the a out the front, there's a whole family. Now take a point on the curve. Well, we've given a good point to use, 0.6, the y-intercept. So sub that into the y function here, our skeletal function if you like. It's a out the front. Put in x is 0, you get -2 squared. Put in x is 0 here, you get 3. Has to come to 6, the y-intercept. So multiplying all that out over on the left, 12a equals 6. A is a half. So we have the family member a half. 3x take 2 squared plus 3. So there are steps here. Do you need to note them down? Okay, perhaps, so that you try to remember them. Alright, I'll give you a go at some of these now and see what you think. Here's some graphs, and the idea is to use the x-intercepts, put an a in front, evaluate the a with a known point on the curve. And I think they're all y-intercepts here, so nice and easy. Okay, pause the presentation, have a go at those, and then I'll show you the answers now. Okay, so here's some results for those functions. Hope you're getting some right. You might have to go back and study it, perhaps read the book again as well. Okay, let's have a look at example 65, and we're nearly at the end. Can you see what we're doing? Here we are, cuts the x-axis again. This time passes through a different point. We use the same approach, only we haven't got the y-intercept now. So the zeros mean these are the factors, reversing the signs there. Then sub in x is 1 and -40. Don't forget the a, because that's what we're going to try and work out now. So a, subbing in -1 in here. Subbing in 1 in there is 1 take 2 is -1. Subbing 1 in here, 1 plus 3 is 4. Subbing 1 in here, 1 plus 4 is 5, equals -40. So multiplying those together, -20a equals -40. Dividing by -20a is 2. So there we have our particular family member. Okay. Alright, so can you do that? Follow those steps. Watch the steps, be aware of what we're trying to do. Maybe note them down. Okay, here's a couple of questions for you. Okay, question 4. I don't think we can get 5 on there. Have a look at question 4. Pause it and scroll forward in a minute as you do them, and I'll show you the answers. Let's just have a look at question 5. It's matching up graphs. So what graph matches little a? Is it big A? I don't think it'll be that easy. Little a, does it match with B, C, D, E or an F? Don't know. So pause it. See if you can match them based on the x-intercepts here and on the graph. But also check the number out in front of those brackets. That's important, by maybe substituting in a value. Alright, pause it, have a go. I'm going to show you the answers now. So there's question 4 and 5 with their particular matchups. Okay, how did you go? Alright, it's all about these forms, isn't it? And knowing the relationship to the graph. Alright, let's have a look at the last little section here. Convert into the general form, which means we're going to expand it. Okay, so that, if you write it all out, here it is, then multiply maybe the first two brackets together using FOIL, or you should see that this is a take b by a plus b, remember that, from back in expansions is a squared take b squared. Okay, so then we've got this one done, and then you can do expansions. FOIL that one by that one. that one by that one, gradually writing the terms down. This one by this one, etc. Okay, and then collecting them up, we get the final expanded or general form. Let's have a look at this one over here. Being careful to leave the neg 2 out the front. X plus 2 by x take 3 squared. We could do this one straight up, or you might have to FOIL it. Hopefully you know, as we said before, a take b squared, all squared, is a squared, take 2ab plus b squared. Okay. Alright, so doing that we get this, or just doing 2 brackets, x take 3 by x take 3, I suppose. Now we have to multiply this out. That's that by that, by the next one, and by the third one. And then similarly, in the second term in the bracket, multiplying by each of those. That's the process of expansion of brackets. Each term in the first by each term in the second. Keeping the neg 2 out the front, collecting up all those terms now, and then multiplying through by negative 2. Negative 2 by x cubed is neg 2x cubed. Negative 2 by neg 4x squared is positive 8x squared. The same here again. Positive 6x. And then by plus 18 is negative 36. So what's that negative sign there? That's very, very important that you don't mess that up. Okay, well they're yours. See what you think. Probably try to do at least half of them. If you've got time, obviously the best thing is to do all of them so that your skills come up quickly. Let's have a look at, we'll pause it, and then let's have a look at the answers. Okay, so there are the answers you're supposed to have gotten. Watch out for these fractions down here in this one. So you've just got to be a little bit careful. Okay, well I hope your skills are coming up, because we want to build on that in future courses, the idea of polynomials, depending on what maths you do later on. But you can see there are some common principles running through there which are helpful in building on your prior knowledge. Alright, well I hope to catch you in another presentation. For the moment, it's cheers from me.